Good morning, students. So, the subject MEMS, in that we have started the unit number 6, that is overview of finite elements. So, let us see which part we have covered. So, in previous sessions we have covered the overview of finite elements method in MEMS. So, early in 1960s, the finite element method in plane stress analysis is entitled in a famous book. So, FAME is nothing but technique which is used to get or to obtain approximate solution of boundary value problems. So, means this is nothing but the procedure is to transform the differential equation into a set of linear equations. So, which can then be solved by the computer in a routine manner. After that, we have covered transformation of physical law into linear equation in FAME. So for that we have seen 8 steps. After that we have seen principles of FEA, that is finite element analysis. Okay. So finite element analysis, just we have discussed that it is nothing but the approximate solutions of boundary value problems. Then we have seen the basic steps involved in carrying out finite element analysis. So from the last chapter, from the last session, we have covered that pre-processing, then conversion of geometric model into finite element model, then assembly and defining the boundary conditions. Okay. So in pre-processing, the geometry in terms of point lines, areas and volume, and in a conversion of geometric model to the finite element model is nothing but the dividing problem into several small elements connected with nodes. That is nothing but the metric connectivity. So the element could be 1, 2 or 3 dimensional and in a various shape. So it is essential that the elements are not overlapping but are connected only at the key points, which are termed nodes, the joining of elements at the nodes. Then that assembly equations are developed for each element, mesh and assembled into. Okay. So after that, defining the boundary condition, that is nothing but the undergo translatory or rotary motion or a combination of the two without experiencing the deformation. Then next is nothing but the loading configuration. So loading configuration means what? Application of force at various points of geometry and its configuration. Okay. Application of force at various points of geometry and its configuration. So after that processing we have to do. So solve the system of linear algebraic equation. The traces are determined from the strain by Hooke's law. Strains are derived from the displacement functions within the element combined with Hooke's law. Okay. So processing solve the system of linear algebra equation. The traces are determined from the strain by Hooke's law. So strains are derived from the displacement functions within the element combined with Hooke's law. So next is nothing but the post processing. The output from the finite element analysis is primarily in the numerical form. So it usually consists of nodal values of the fields variables and its derivatives. So for example, in solid mechanical problems, the output is nodal displacement and element traces. Okay, what is post processing? The output from the finite element analysis is primarily in the numerical form. So it is usually consists of nodal values of the field variables and its derivatives. So for example, in solid mechanical problems, the output is nodal displacement and element traces. Okay. So this is nothing but the basic steps involved in carrying out the finite element analysis. There is a pre-processing, conversion of geometry model into finite element model, then assembly, that is material properties that are representation, then defining the boundary conditions, loading the configuration, processing and post-processing. Okay, so in the pre-processing we have seen that the construction of the geometric model. Okay, so in terms of the points, lines, areas and volume. Then the conversion of that geometric model into finite element models. Means how discretization is the process of dividing problem into several small elements and connecting it with the nodes. So such a number of nodes are put into the setup of the matrix connectivity. Okay, so the elements could be 1, 2 or 3 dimensional and in various shapes. Okay, so it is essential that the elements are not overlapping but are connected only at the key points, which are termed as the nodes. Okay, so the joining of elements at the nodes and the eliminating duplicate nodes is termed as the meshing. Then we have seen the third, that is assembly material property data representation. So here equations are developed for each element in the FM. So mesh and assemble into a set of global equations that model the properties of the entire system. Then the minimum material properties required are Poisson's ratio and Young's model. So defining the boundary conditions. Boundary condition means that suppose an element is constructed on the computer and a force is applied to it, it will act like a free floating rigid body and will undergo a translatory or rotary motion or a combination of the two without experiencing the deformation. So to study its deformation, some degrees of freedom must be restricted. So for some of the nodes, so such a constraints are termed boundary conditions. Then loading of the configuration, so application of force at various points of the geometry and its configuration. So after that processing, so solve the system of linear algebraic equation. The stresses are determined from the strains by Hooke's law. Strains are derived from the displacement functions within the element combined with Hooke's law. So post-processing, the output from the finite element analysis is primarily in the numerical form. So it is usually consists of nodal values of the field variables and its derivatives. So for example, in solid mechanical problems, the output is nodal, displacement and element traces. So there are some common finite element applications. So which are they? Let us see. So in a mechanical system, aerospace, civil, automotive. Okay. Then in an engineering structure, stress analysis, static and dynamic. Then again in suppose linear and non-linear fluid flow also the finite element analysis is applicable. Then heat transform, electromagnetic fields, soil mechanics, acoustics, biomechanics. Okay, so common finite element analysis, that is mechanical, aerospace, civil automotive, engineering structure, stress analysis, then static dynamics, so linear, non-linear fluid flow, heat transform, electromagnetic fields, soil mechanics, acoustics, biomechanics. So these are some common finite element analysis applications. Then next, that is modeling of coupled electromechanical systems. Okay, modeling of coupled means electronics as well as the mechanical. So that coupled between that and it is nothing but the modeling of coupled electromechanical systems. So a modeling procedure is proposed to handle strong electromechanical coupling appearing in micro electromechanical systems. Okay, so a modeling procedure is proposed to handle strong electromechanical coupling appearing in micro electromechanical systems. So the finite element method is used to discretize simultaneously the electrostatic and mechanical field. Okay. So for that domain, the micro electromechanical system, we have to combine the electronic and mechanical systems together. So for that, modeling procedure is used to handle the strong electromechanical coupling. Okay. So through the finite element method, is nothing but the discretize simultaneously the electrostatic and mechanical fields. So the formulation is consistently derived from variational principles based on the electromechanical free energy. Okay. So the formulation is consistently derived from variational principles based on the electromechanical free energy. Okay. So the formulation is consistently derived from the variational principles based on the electromechanical free energy. So in classical weakly coupled formulation, okay, in classical weakly coupled formulations, staggered iteration is used between the electrostatic and the mechanical domain. Okay. So in classical weakly coupled formulations, staggered interaction is used between the electrostatic and the mechanical domain. So therefore, in those approaches, linear stiffness is evaluated by finite differences and equilibrium is reached typically by relaxation techniques. Okay. So therefore, in those approaches, linear stiffness is evaluated by finite differences and equilibrium is reached typically by relaxation techniques. Okay, so in a modeling of coupled electromechanical systems, a modeling procedure is proposed to handle strong electromechanical coupling appearing in micro electromechanical systems, that is MEMS. So the finite element method is used to discretize simultaneously the electrostatic and mechanical fields. So the formulation is consistently derived from variational principles based on the electromechanical free energy. Okay. So in classical weakly coupled formulation, staggered iteration is used between the electrostatic and the mechanical domain. So therefore, in those approaches, linear stiffness is evaluated by finite differences and equilibrium. So is reached typically by relaxation techniques. So, the strong coupling formulation presented here allows to derive exact tangent matrices of the electromechanical system. Okay. So, as we discussed, there is a electro and mechanical coupling. So, the strong coupling formulation presented here allows to derive exact tangent matrices of the electromechanical system. Thus, it allows to compute non-linear equilibrium positions using Newton's Raphson type of iterations combined with adaptive meshing in case of large displacements. Okay, so thus in a strong coupling formulation, if it allows to compute the non-linear equilibrium positions using Newton's Raphson type of iterations combined with adaptive meshing in case of large displacements. So furthermore, the tangent matrix obtained in method exposed in this paper greatly simplifies the computation of vibration modes and frequencies of the coupled system around equilibrium configurations. Okay, so furthermore, the tangent matrix obtained in the methods exposed greatly simplifies the combinational of vibration modes and frequencies of the coupled system around equilibrium configurations. So the nonlinear variation of frequencies with respect to voltage and stiffness can be then be investigated until cooling appears. Okay? So the nonlinear variation of frequencies with respect to voltage and stiffness can be then be investigated until cooling appears. Okay, so let us see the following section outlines how the fully coupled finite element approach can be devised by applying a variational approach based on the free energy of the electromechanical system. Okay, so here one example we have considered, that is classically weakly coupled procedure. It is shown in the left side compared to the proposed strongly coupled approach to the right side. Okay. So here initial level structure fixed solved electrostatic fluid, that is BEM. So determination of traction on the structure. So solve the structure by using finite element method and then check the convergence. Okay. The ratio of this taken into the multiplication. So if it is updated, then update the call. Okay, and once again with the updated information, again it will be start that the full coupled weakly coupled procedure. And conversion, if it is matches, then the end of the procedure. Compared to this, here strongly coupled approach is shown. So here at the starting initial configurations are used. So solve coupled problems linearize around new configurations. Okay, means after the solving that the coupled problem linearized around new configuration, that is finite element methods. So then check the convergence, and again if there is a mismatch, then update the code and once again the solve coupled problem linearized around new configuration, and after that procedure will be stopped. Okay, so this is nothing but the fully coupled infinite element approach can be devised by applying a variational approach based on the free energy of the electromechanical system. Okay, so we have started with the modeling of coupled electromechanical system. So in that, a modeling procedure is proposed to handle strong electromechanical coupling appearing in micro electromechanical system. So the finite element method is used to discretize simultaneously the electrostatic and mechanical fields. Okay, so the formulation is constantly derived from variational principles based on the electromechanical free energy. So in a classical weakly coupled formulation, staggered interaction is used between the electrostatic and the mechanical domain. So therefore, in those approaches, linear stiffness is evaluated by finite differences and equilibrium is reached typically by relaxation technique. Okay, so from that the strong coupling formulation presented here allowed to derive exact angular matrices of the electromechanical system. So thus it allowed to compute nonlinear equilibrium position using the Newton-Raphson type of iterations combined with adaptive meshing in case of large displacement. So furthermore, tangent matrix obtained then simplifies the computational vibration models and frequencies, and the non-linear variation of frequencies with respect to voltage and stiffness can be investigated until the pull-up in appears. So here we have seen the weakly coupled procedure as well as the strongly coupled approach. Thank you.